Hi students, I am Simha Verma, your chemistry faculty. So here I would like to explain physical chemistry, and I have chosen the topic called chemical kinetics, and it is very important. Every year you can expect one question or two questions. Okay, most probably we are supposed to get two questions every year. So this is very important topic. So guys, here in this video I would like to explain only formulas, okay, not definitions, not any other things, okay, only formulas, and where we have to apply those formulas I is supposed to discuss in this video. So directly I have written here one equation. So here you can see the equation 2a plus 3b gives rise to 2c. So here ROD is nothing but disappearance, okay, D is nothing but disappearance, guys. Okay, so I am writing here D is nothing but disappearance, okay, and reactants we have A and B. So with respect to reactants, rate of disappearance of A, rate of disappearance of B, it is nothing but minus d of A divided by dt equal to minus d of B divided by dt. Okay, what is meant by this d? This d is nothing but change in concentration with respect to time. Okay, change in concentration with respect to time, or you can also write something like minus delta A divided by delta T. Okay, here also you can write here minus delta B divided by delta T. Okay, and here minus sign, it is very important to note here, okay, because reactants concentration with respect to time decreases. So this sign indicates reactant concentration decreases. And now let's come back to the products. Products we have C here. So formation, F is nothing but formation, guys. Okay, so here I am writing F is nothing but formation. So products will form now, so that's why rate of formation of C plus d of C divided by dt. Here plus sign indicates products increases, concentration of products increases, so that's why I have kept here plus, and minus sign concentration of reactant decreases, that's why I have kept here minus. And try to remember here 2 3 2 stoichiometric coefficients you should not take with respect to rate of disappearance, rate of disappearance, rate of formation, no stoichiometric coefficient. And if you want to write rate of reaction, overall rate of reaction for the given equation, it is nothing but minus 1 divided by 2. You have to take stoichiometric coefficients in the denominator with respect to minus d of A divided by dt, and minus 1 by 3 d of B divided by dt, and plus 1 by 2 d of C divided by dt. This is nothing but rate of reaction. Okay, it's nothing but rate of reaction. So now let us go to some important points what we have concluded here. Reactant concentration decreases with respect to time, product concentration increases with respect to time, intermediate concentration remains constant with respect to time. Okay, this particular last point you will be coming to know at the end of this chapter. Okay, next we have discussed one rate of reaction here. I have written first rate of reaction with respect to differentiation, okay, with respect to change. Okay, this delta is nothing but change. Okay, D is nothing but differentiation. With respect to differentiation I have written here. And one more thing, we have one more rate law for the same equation. For the same equation, if you want to write rate law, so it's nothing but I have taken the same equation, R equal to K, A to the power X, B to the power Y. Clear? And here X and Y, if you add, it's nothing but order. Okay, and this order can be 0, 1, 2, so on, and it also can be fractions, like it can be positive or it can be negative also. Try to remember, it's very important, it can be 0 also. Okay, so here this is nothing but order, and this order is experimental quantity. Okay, this X and Y can be stoichiometric coefficient. This X and Y, X comma Y can be stoichiometric coefficient, or it cannot be. Okay, or it cannot be, guys. Okay, so if you talk about units, Okay, by the way, this K is nothing but rate constant, this R is nothing but rate of reaction. So K equal to, see, I am writing the units of concentration. Concentration we already know, mole per liter, and rate of reaction it's nothing but mole per liter per second. Okay, and K units will be what? So from here what I can write, let me write here, K equal to R, rate of reaction, divided by A to the power x, B to the power y. So rate of reaction, keep this one, and A to the power x, B to the power y, you just substitute this value. Okay, if you want I will solve in the bottom here. So here what we supposed to get, K equal to rate of reaction is nothing but what? Mole, M I am writing, divided by liter. Okay, rate of reaction second, divided by A to the power x, it's nothing but mole to the power x and mole to the power, mole per liter to the power y. So here what you will be getting, mole per liter, this we can take 1, so you will be getting 1 minus x plus y, second inverse. This x plus y is nothing but what? We already know that x plus y, it's nothing but order. So mole per liter 1 minus n, second inverse. So guys, this is the units of K, and it's very very important. Okay, so hope this page you have understand. So I am going to the next page. And guys, so we have concluded what? R equal to K A to the power x, A to the power n is nothing but order. I said n can be what? 0. So keep n equal to 0. So you will be getting R equal to K. And here what you got here, concentration is not there, and rate of reaction is completely depending upon constant. So what we can conclude, it is independent to concentration of reactant. Okay, and here I have skipped the derivation of integrated rate law for zero order reaction. So directly I am writing the law here. AT is nothing but concentration of reactant at a time t, and K is rate constant, T is nothing but time, and A0 is nothing but initial concentration. Okay, I think you already know this formula. Okay, it's very very important. And let's go to half life. Half life is nothing but what? Half life is nothing but time will become half. Okay, and concentration will become half of the initial concentration. Means you have to take that concentration which makes initial concentration half. If you substitute these two values here, then you will be getting this formula. Okay, this is called T half. Half life. Okay, here I haven't written. Half life is directly proportional to initial concentration of reactant. Okay, T half directly proportional to A0. We can write now here this constant if you remove means. So here T half, it is directly proportional to A0. Very very important formula this one. Okay, next one. Let us talk about degree of dissociation. Alpha. Alpha value, it's well known symbol alpha. This is nothing but degree of dissociation, and here they will be giving the formula, number of moles reacted divided by number of moles taken. How many moles reacted? It's nothing but x. Means, for example, let us take this equation. So I am trying to explain you here itself. A gives rise to B. At time t equal to 0, let us take initial concentration A0, and we already know it will be 0. Okay, and after some time t dash, A0 minus x will be reacted, and here you will be forming some x product you will be forming here. So number of moles reacted is nothing but x only, no? X moles got reacted, and number of moles taken is nothing but A0. So x divided by A0. So what is meant by this x? This x is nothing but concentration of B at the time t. Did you observe here? That x is nothing but concentration of B, concentration of product at time t. So here let us substitute here. Okay, let me make you understand. This is nothing but integrated rate law, no? So take that integrated rate law, and here AT is nothing but A0 minus x. This particular thing is nothing but concentration of A at time t. This is nothing but concentration of B at time t. So BT I am taking here. So a naught minus x equal to minus kt plus a naught. So directly a naught got cancelled, x equal to kt, minus minus also got cancelled. So substitute here, you will be getting alpha value, and t 100% is nothing but a naught divided by k. Okay, a naught divided by k. Simple here. T 100%, how you can write here? It's nothing but t 50% plus t 50%. T 50% is nothing but half-life. So let us go with respect to graphs, guys, here. So here what you have the graphs here? Rate with respect to concentration of reactant going straight line. Why? Because we have got what? Because we have got here R equal to K, a to the power 0. Okay. So we have to draw this straight line, because a to the power 0 is nothing but 1 only, no? So R equal to K, which is independent to concentration of reactant. And here let me discuss about concentration of reactant. Okay, we have this particular equation, na? So take y equal to mx plus c, something like that, and you can get the slope, and you can draw the graph here, something like this you will be getting. And let us talk about concentration of product. Concentration of product x and time t, you will be getting something like this slope equal to minus k. Okay, hope these three graphs are clear. Okay, and let me go to the next slide. And here t half, this one let me explain. T half, what you got? T half equal to a naught divided by 2k, keep here 0. So it's nothing but y equal to mx plus c. So c equal to 0, that's why I have started from here. Okay, and here y is nothing but t half, so I kept y, and x is nothing but a naught, and here slope you have got slope equal to 1 divided by 2k. Okay, and here this is very important for your Neet point of view, guys, so pay attention here. So here let me explain you. For example, we have a naught, initially we have 100. From this 100, for example, if it is going to 90 and it is going to 80 and it is going to 70, means here we have seen what? 10% decrease. Okay, for every case we have seen 10% decrease. 10% decrease, let me take the time t. From 100, if it is going to 80, it's nothing but 20%, you will be getting 2t. From 100 to 70, it is nothing but 30%, 3t, and it will keep on going on. Okay, till 0 you can do the same pattern. Till the 70 becomes 0, you can follow the same pattern. Make a note, it should be first order. Okay, and we got here what? We got half-life equal to how much? T half equal to a naught divided by 2k. Clear? So here 100, half of 100 is nothing but 50. 50 half is nothing but 25. 25 half is nothing but 12.5. 12.5 half is nothing but 6.25. Clear? So here 100 to 50, it is nothing but t half, and 50 to 25, it is t half divided by 2. Why? Because see here, I have written here already, t half is directly proportional to a naught. If a naught is becoming half, then t half also become half, na? Come on, guys. A naught I am making divided by 2 in all the cases. Okay, 100 divided by 2, 50, 50 divided by 2, 25, 25 divided by 2, 12.5, like that I have divided by 2, means t half also I have to make it divided by 2, na? Because both are directly proportional. Okay, okay, here t half divided by 2. From 100 to 25, how much is the remaining? 25% is remaining. How much it got consumed reactant? 75%. So T 75% equal to this one plus this one. You have to add these two. Okay, if you add these two, you will be getting 3 by 2 T half. Clear? From 100, if you want to calculate till here, it's nothing but how much? This is remaining, this is reacted. 87.5 equal to, just add all these 3, you will be getting 7 by 4 T half, and after that T 93.75. How we got? 100 minus 6.25, which is nothing but 93.75. This is what remaining. how much it got reacted. I have said that x na, that x is nothing but this one only, 93.75 equal to, if you add all these 4, you will be getting 15 by 8 t half. Okay. And in case of zero order reaction, r, units of r equal to units of k. Okay. Hope, I think this is clear. Okay. Yeah. Next we will go to the most important topic in chemical kinetics. Okay. And here the questions will be asked just from the concept itself, guys, and the concept is very easy. Let us focus on first order reaction, r equal to k a to the power n, okay, n equal to 1. So integrated rate law, if you do differentiation, etc., etc., you're supposed to get total 3 equations. First equation, second equation, third equation. Okay, so we can draw the graphs related to these 3 equations. So I'm skipping that derivative part. So let us focus k. Okay, from here you have k value, see here, from this k equal to you can calculate, from this t equal to you can means you can keep only t on LHS and you can make all the components on the other side, LHS equal to RHS. Likewise you can get t as well as k. If you calculate here t half, I already said na, t should become t half and AT should become A naught divided by 2. Then you will be getting this particular equation. Did you observe here T half? Nothing is there here. No concentration of reactant, no concentration of product, no concentration of intermediate, nothing is there here. Okay, we have got simply 0.693 divided by K. And T 100% is not defined, guys, here. Okay, so if you want, let me do that case here. K equal to 2.303 divided by, let me take here T, K log to the base 10, A naught, let me take here 100. Initially we have taken here 100, and this AT is nothing but what? 100 minus x. X is nothing but 100 only, no? So 100 minus 100, you will be getting 0. Okay, so 2.303 divided by K log to the base 10, 100 divided by 0. It's nothing but what, guys? 100 divided by 0 is undefined, no? You will be getting infinity. Okay, you will be getting infinity, which is undefined in short. Okay, means T 100% is not defined for first order reaction. T 99.9% is defined. You will be getting something like this value. Okay, with respect to T half 10, with respect to T half 99, this is 99.9%, 6.6, T 90, 3.3 into T half. Okay, and T 99, 2 into T 90, T 75, 2 into T 50%, T 25, 0.414 into T half. Okay, something like this we supposed to get. Okay, let me go to the next slide. Okay, so here let us focus on the graphs. Some of the graphs let us focus here. So here what we will be doing here, the first thing, r equal to k a plus 0, y equal to mx plus c. Okay, if you apply here y equal to mx plus c, you can get the graph, something I have drawn in the bottom. And this is what integrated rate law for first order reaction, AT equal to A naught e to the power KT. So this A is nothing but what? Concentration of reactant only, no? And this AT is nothing but concentration of reactant. So this AT I have substituted here A. So r equal to k A naught e to the power minus KT, and here you are supposed to get the graph something like this. Okay, try to keep, guys, here, keep just put t equal to 0 and t equal to infinity. Basic maths you just apply, you will be getting the graph something like this. Keep here t equal to 0 and keep here infinity. Okay, and let me go to the third one. Okay, third one I have taken this particular top equation and I have drawn this graph. Same thing, try to keep here t equal to 0 and try to keep t equal to infinity, you will be getting the bottom graph. Okay, and with respect to natural log also I have taken here ln AT equal to minus KT plus ln A naught. So in this case also we are supposed to get something like this, keep. Okay, here also keep the values. Okay, and this is with respect to natural log, this is with respect to log. to the base 10. Okay, this particular equation is helpful for problems also. Okay, and the graph of this particular equation I have drawn in the bottom along with slope. And let me take here, this x is nothing but what? Concentration of product. Okay, same thing I have said you know, a naught minus x, this x is nothing but concentration of product. So a naught minus x, a naught e to the power minus kt. So try to make the arrangements, you are supposed to get x equal to something like this. So I have got the graph here, concentration of product versus time, and here also try to keep t equal to 0 and try to keep t equal to infinity. Then you will understand why I have drawn the graph something like this. Okay, I have drawn curves because exponential graphs all these are. Okay, this is exponential graph, this is exponential graph, this is exponential graph. Okay, all these are exponential graphs. Okay, the same pattern let me discuss with respect to first order. Okay, so 100 going to 50, 25, 1, 12.5, 6.25, and here what you have got, t half equal to what? T half equal to 0.693 divided by k. This is the t half value we got in the first order reaction, and here there is no initial concentration, it is independent to initial concentration, no? So directly we can keep here all the cases t half. Okay, most of them will be multiplying here 1 t half, 2 t half, 3 t half. It's not like that. Okay, 100 to 50 t half, 50 to 25 t half. If you want to go 100 to 25, then 2 times t half. Clear? If you want to go 100 to 25, 2 times t half. If you want to go 100 to 12.5, it is 3 times t half, 4 times t half. Okay, let me explain in brief. So 100 to 25, let me take here. This is remaining. Okay, this is remaining. How much it got reacted? 75. So T 75 equal to 2 T half. And let me take this one. Okay, how much this is remaining? How much it got reacted? 87.5 equal to 3 times T half. 6.25 remaining. How much it got reacted? 93.75 equal to 4 times T half. That's it, guys. Okay, the same thing I also written where the same thing I have written here also. Okay, you just observe in the previous slide. Okay, here I have taken here some of the relations, okay, with respect to T half as well as T90, T99.9%, etc. Okay, and here from here you can understand percentage of reactant left after n T halves. See here, nothing is there, guys. 100 divided by 2 to the power n. Let us take this n. Here 1 T half is there. See here, let me make it down. For example, keep here 1. 100 divided by 2, 50. You are getting. Here keep 100 divided by 2 square, n equal to 2. Okay, try to keep here n equal to 1, 2, 3, 4. Okay, if you keep 1, you will be getting 50. If you keep 2, you will be getting 25. Okay, 100 divided by 4, 2 square, 4, 25. 100 divided by, keep n equal to 3, 2 cube, you will be getting this one, 4, you will be getting this one. Means we have got something like this. In short, we can say A naught divided by 2 to the power n. A naught is nothing but what? Initial concentration, which I have taken 100 in the above case, and I have represented percentage here. That is left, I said na, remaining. These all are remaining. If you want to get 75%, what we will do? 100 minus 100 2 to the power n. Keep n equal to 2. 100 divided by 4, 25. 100 minus 25, which is nothing but 75. We are getting the same pattern. Keep here n equal to 1, 2, 3. You will be getting left as well as reacted also. Okay. And here let us go to next case. Here one more important, very important, guys, here in case of first order reaction. Okay, we have to go with respect to gases also. questions can be asked here. A gas gives rise to B plus C. Initial pressure, let us take P naught, 0, 0. We already know no? At time t equal to 0. At time t equal to some t dash, you will be having this P naught, we will be having some decrease, and here we will be having some increase, which is nothing but 0 plus P, 0 plus P. Products increases, that's why plus. Okay. So this whole is nothing but P total, na? So P total equal to, I have written here, make it cancel, and you have got P equal to P total minus P naught. Put it aside. Write first order reaction. In case of A naught, just take P naught minus P. So here P naught minus P, we have got this one. So substitute this value here, we'll be getting something like this. Okay. So what we have got here, K equal to, if you substitute that one, you will be getting something like this, and it is very, very important. Try to remember P naught is nothing but initial concentration, initial pressure, and P total is nothing but total pressure. Okay. After some time, whatever pressure we have, that is nothing but P total. T is nothing but time, K is nothing but rate constant. And here nth order also, do the basic derivation, apply basic mathematics, you are supposed to get the equation something like this. Okay. Basic differentiation formulas will be involved in between the derivation also, it's not much complicated, just have a look on that. This is nothing but nth order reaction, and T half, same pattern, how we have solved 0 order, nth order, like this. And these two, it's not applicable for first order reaction. Okay, not applicable for first order reaction. Clear? And guys, did you observe? So T half we got nth order, this is very, very important guys, very, very important statement. T half, did you observe here? T half equal to 1 divided by A naught n to the power minus 1. I have taken the same thing here, or I can also write this one. Okay, n minus 1, if it go to numerator, 1 minus n. Okay, let me go with respect to this particular formula. Okay, n minus 1, what we supposed to get here? T half for the first one, T half of the second one, inversely proportional na. For 1 you will be having in the denominator 1, so for 1 you got in the denominator 1, for 2 you will be taking in the numerator 2. A naught is nothing but initial concentration, n is nothing but order, and this is half life. And next most important concept, it is Arrhenius equation. So guys, here also theory, it is very, very important. Okay, without theory you cannot understand what is activation energy, what is rate constant with respect to temperature, how it will be varying. Okay, so here I am skipping the theory. Okay, so here I have written some formulas related to Arrhenius concept also. So K equal to A E to the power minus EA divided by RT. Exponential, E is nothing but exponential, Arrhenius constant, rate constant, activation energy. Okay, universal gas constant, temperature. If you apply, in this case, if you apply natural log, you will be getting this formula. If you apply log to the base 10, you will be getting the down equation. Very, very important, this one. Clear? Okay. And if you draw the graphs, okay, with respect to log to the base 10, okay, simply here what is there here? Here just try to apply y equal to mx plus c. Here also y equal to mx plus c. Okay, so you will be getting the graphs here. Okay, first graph, second graph, natural log with respect to 1 by t, log to the base 10 with respect to 1 by t. Okay guys, now here let us take here temperature T1, take K1, temperature T2, take K2. Clear? So here you will be getting something like this equation. Okay, most important for problem solving case. Okay, in chemical kinetics they will be giving different temperatures T1, T2, and they are supposed to ask you activation energy. They will be giving activation energy, and they can ask you K2 divided by K1, or they will be giving K1, they will ask you to find K2, etc. Those kind of questions will be asked here. So case 1, keep EA equal to 0, you will be getting K2 divided by K1. Clear? Hope I think no need of explaining it. If you want, let me write here, log to the base 10 K2 divided by K1, which is nothing but 0. If you keep here EA equal to 0, this whole term will be getting 0. Log to the base 10 K2 divided by K1, log to the base 10 1. One value only, no? Log 1 value only 0. Cancel, cancel. So K2 equal to K1. Clear? So you will be getting K2 equal to K1. So here we have got something like this. And case 1, try to keep activation energy equal to plus. Means this whole term will be plus. Means log base 10 K2 divided by K1 will be greater than 0. Okay. Let me do it here. Log to the base 10 K2 divided by K1 will be greater than 0. This 0 is nothing but log to the base 1. So log will be getting cancelled. So you will be getting K2 greater than K1. Clear? You will be getting K2 divided by K1. That is what I have written here. And same thing. Try to keep here EA equal to negative. You will be getting the same equation. K2 less than K1, T2 greater than T1. Okay. Now let us discuss with the catalyst. If you keep catalyst in a reaction, if you do the reaction with respect to catalyst, activation energy will be very, very less and rate of reaction will be very, very high. Okay. And without catalyst, activation energy is very high and rate of reaction is very low. Rate of reaction is low here and here rate of reaction is high. Try to remember, guys. Okay. So the same thing I have taken with the catalyst K2 comma EA2, without catalyst K1 EA1. So if you substitute there, you will be getting something like this. Don't confuse with the top equation. This is with respect to temperature. Okay. And here I have written with respect to activation energy. Hope you got. Okay. And last slide. Okay. So here see guys, this is also very, very important topic here. So here I have taken irreversible reaction. Okay. Reactant means y-axis energy, progress of the reaction. Reactant will be having at 0 some energy will be there, na? Clear? So that energy I have taken here ER. If you provide some energy, to activate the reactant, whatever energy we are providing, that is nothing but activation energy, and I have written here something like this. I have given activation energy to this reactant, it crossing the barrier and it suddenly came till down. Okay. And in the side graph from here I have given activation energy. I am just activating reactant. I want product now. I have to activate. So for activating, I have to make this reactant to cross the barrier. So I am giving activation energy and it stopped top. Here it came bottom and here it stopped top. Clear? So in this case, which is greater? ER is greater, na? That's what I have written here. Okay. ER is greater. Delta H formula is EP minus ER. Okay. And here which is greater? EP is greater. So that is what I have written. Delta H formula will be EP minus ER. Okay. EP minus ER. Okay. So here what? ER is greater, but ER is in negative. So negative exothermic irreversible reaction. First case done. And in the second case, EP is greater, positive endo irreversible reaction. First graph, second graph. Irreversible case we have done. Let's go to reversible case, guys. Okay. Here in case of reversible reaction, reactant go to product, activation energy forward we supposed to call it as, product going back to reactant we supposed to call activation energy backward, EAB EAF. Clear? Same thing I have written. The same thing whatever happened in the top, the same graph, whatever happened in the top, I have drawn in the bottom also. Clear? Same thing, but I have taken reversible sign. Okay. So EP minus ER will be negative, exothermic we are supposed to get, and delta H also we have to get negative, guys, because this is negative. This is exothermic graph. Okay. So which is greater? EAB is greater. Okay. This is these two are the very important. EAB is greater. Okay. So try to frame this particular thing in such a way that you have to get negative. EAF minus EAB. Then you will be getting negative, no? Because EAB is greater. Then only you will be getting negative, and this particular graph is nothing but exothermic reversible reaction. And let's come back to the side case. Delta H positive, and frame here in such a way that you have to get positive. Okay. Here which is greater? EAF is greater. Here EAB is greater. Okay. So here positive, this is nothing but endothermic reversible reaction. Okay. So guys, these are some of the formulas in chemical kinetics. Okay, means it will be helpful for your Neet examination. Okay, in the last moment, if you want to do a quick revision of all the formulas in chemical kinetics, this video will be helpful. Okay, and don't forget to revise theory which is given in your NCERT. Once have a look on the theory. Okay, hope you understand the video.